walkthrough for From Social Science to Data Science by me, Bernie Hogan. This is Chapter 9 on Visualizing Expectations. So, of course, you can't really have a book on some sort of data science or programming topic without talking about visualizations. Pictures, images, they really help tell a story. They help give us some intuitions and can really drive home a point. But they're not necessarily going to be the only way you want to make a claim, or they're not going to be the only way that you're going to want to demonstrate some sort of scientific concept. And so to that end, I like to make this a chapter about how we pair visualizations with some statistical reasoning in order to really give us a sense of not just what we see there, but whether what we see is itself a difference that makes a difference. So I first want to lean on a quote here from an old mentor of mine, and this is Ben Schneiderman. He says, the purpose of visualization is insight. It's not pictures, and that's really the point here. We don't want to make a visualization that's overly complicated or overly detailed, simply to demonstrate that we have the data. What we want visualizations to do is really to help explain or demonstrate a point or help give us an intuition. So today our learning goals are, first we're going to want to produce a distribution from a random number generator. And so that's, because this is not just going to be any type of visualizations we're focusing on, but really visualizations of distributions. So we're going to want to first produce them and then plot such a distribution. We're going to look at matplotlib, and there's going to be a little bit of Seaborn in there. This is an additional package for Python and for pandas in addition to matplotlib. It draws upon matplotlib, and they work nicely together. We're going to want to understand how a trend line or a regression line can be calculated. We're not going to drill too deeply into regressions here, but we do want to get a sense that if we draw a trend line, what does that mean, and how much can we trust that trend line? We're going to want to annotate a figure with some interesting details, and those might be based on expected values and confidence intervals. So not just having the first chart that we have up there, but kind of massaging that chart a little bit so that we really accentuate the things that we want to claim or want the reader to pay attention to. We're going to want to use some statistical tests to compare two groups. So I'm just going to briefly mention t-tests and ANOVA, but not really going to cover that too deeply. And the same thing, we're going to want to look at two distributions from the same group. So that might be like a correlation or a regression type of thing. And we're going to want to consider the elaboration model for some multivariate work. So to start off, I'd like to lean on a classic distribution within statistics, and this is Anscombe's quartet. This one is, it's really played out. You'll see it in a lot of books, but I think it really works. And when I first saw it, I thought it was quite beguiling in a way. So here we can see that we have these four different distributions, and pretty obvious right here that they all have a slightly different shape. This one's curved, this one's kind of distributed around the line. This one right here has this outlier at the top, and this one here has an outlier over here. But you see that they have slightly different, distributions of points there. But yet, each one of them has a really similar mean, median, and standard deviation. So if we look down here in the table, they all have a mean of 9, in this distribution. They all have a count of 11. There's 11 dots. And a standard deviation of 3.317, and that's for x. So for x is the same for all of them, except for number 4, there's a slight difference right there. Now for y, for the y values, again, they're all pretty much exactly the same on the mean. Same count, very, very close in the standard deviation, and the median is just a little bit variable there, but as you can see, it's still very, very similar. So if you're just looking at the table, you might not really get a sense of the difference between these different distributions. Just these measures of central tendency don't necessarily tell us about the shape, but the visualization, the shape became very obvious. And so in the first one, this would be just like a trend line right here. We'd want to keep this as is, but the line might be a bit noisy. Here we'd want to use something like a polynomial. So you can take a number and the square of that number, and then when you plot that, you'll get kind of this curve type shape. We might want to consider how we would remove an outlier right here, and similarly right here, would we want to remove an outlier, or do we want to think of this outliers representing maybe a different class, or otherwise investigate the measurement somehow. But really, we don't want to just equate these two because the difference is so dramatic. So let's have a look at that in Jupyter Lab right here. And once again, as usual, we go right up to the top and kernel, restart kernel, clear all outputs. Nice clean copy here. And okay, very good. So I'm going to start here. And today, before I get into it, I want to actually talk about the things that we're importing. So we're going to use NumPy. That's the numerical Python package, and we've seen that before for arrays, but now we're going to see some number generation going on. We're going to want to use a matplotlib, and you'll notice here I import matplotlib.pyplot as plot, PLT. So you'll see a lot of like PLT objects, and in fact, whenever we initiate a visualization, and that's through a number of different ways, a PLT object is just created along with it. And here's Seaborn. Now, in the code, in the version you have, you probably have this not commented out. I did that myself because I want to show this. First, we're gonna import these three up here, and now let's look at that Anscombe's quartet. Let's look at the data now. The reason why I had this comment, and I want to show this down here, look at this drawing. It's in, by default, it's in PNG, a portable network graphic. It's a decent format, but it's rasterized. And what rasterized means is that it represents this as an array of values, and that array of values thus is mapped to the size, is mapped to that particular image. What does that mean? Well, look what happens when we zoom in. It doesn't really get any sharper. It's quite blurry there. And so that blurriness represents the sort of compression of the image. Now you can make a bigger PNG if you want, and so that will make it more detailed. But ultimately, I think it's useful to take advantage of what's called structured vector graphics, and those are the graphics are going to be sent to the screen literally as a set of like lines, as glyphs or curves, and that they will just be rendered on the screen. So just watch what happens when we include that, and then we'll do this again. You can see, okay, so it's much sharper. Immediately we can tell it's much sharper. Now look what happens when I zoom in. Now if I zoom in, I keep zooming in, and it's just crisp and it's clear. So the thing is that you may have an academic paper, some sort of research work where you want to share this with other people, and there might be a lot of detail on the screen. If you show this or export it as a rasterized image versus a vectorized image, then you know, you can run into trouble with the graphic warping or getting fuzzy or being hard to read. Now you'll notice that what I don't do here in this document is save these figures. Yet I did do that in order to create the book. So before we go on, I just want to show that here, and that's plt.savefig. And now what we put in here is the path. Now I'm gonna cheat a little bit. Instead of my normal using the path object and data, I'm gonna create a demo, and then I'm just gonna delete that demo here. And you can see I've actually already practiced that. So demo.png. And let's watch this again. I'm going to do that and then go .pdf as well. Now we're going to see that it's going to save both of them because they're both code. You know, we'll refresh this. Let's see they're there. We double click on that, and there's our PNG image, and we can see it all of its blurry glory. And here's a PDF. Now, PDF, if you didn't know, is also a vectorized format. So a PDF like SVG can show this, and it'll be like really clear even when you keep zooming in and so forth. Another thing about PDF that's really nice is that you can then drag that and drop it into modern word processors, such as, you know, the most recent Word or Calc, and it'll work the same way there. It'll still be there, and it'll still have that nice vectorized feature. But of course, if you want to go on and do some really robust work, you might want to do this in LaTeX. And again, in LaTeX, it really is excellent to have your stuff in either an SVG or a PDF, because when you render it on the screen, it'll look great. Okay, I'm going to delete those right here. And indeed, that's it. Now, before we go on, we saw that table there on in the PowerPoint, but I want to show it here. And the reason I want to show it is because it's an example or an opportunity to see a group by operation. You might be wondering, like, when do we use those? And what we can see here with the data set, in the data set, it has an X and a Y value. So we group by, and then just look, with this .ag, You can see here a mean, count, standard deviation, and median. And so it groups by data set 1, 2, 3, and 4, and does all of this. Now, in case you don't have a good mental model of what it looks like otherwise, here we are. It's just data set 1, 2, 3, and 4, and then there's the x and y coordinates. So then we sort of like squish down, group data set 1, and we do it, and we use these aggregating functions, and then y, similarly, the same thing. You'll also notice down here I did styled out format. Now finally, I do want to notice, or I do want to point out that this way of doing with the periods at the beginning, you can just do it here. You don't even need to have a function in there, and this will just run these sorts of things like so. I mean, the spacing won't really matter for this, and you just look, it shows up the same. Now, of course, this won't be assigned as an object, but unless you do so. But you can thus use those parentheses on the either side of these kind of long statements in order to break them up over the lines and maybe make it a little bit easier to read. Okay, so distributions. I guess we have a sense then that it really makes a lot of sense to visualize them. On the right here, we can see a whole ton of different examples from Matplotlib. Now, they help us understand a shape and therefore how expected an expected value is, as well as how confident we are in that value. There are many visualization types, aesthetics, colors, details, and features available. And you can see that in Matplotlib as well as others. But they're only really as good as our ability to confirm that the insights we observe are not just artifacts of the visualization process. If they are, then it doesn't matter that we have lots of cool visualizations. We're just kind of showing off and not actually helping to communicate some sort of claim. So the visualization gives us an intuition that we can then test statistically, or at least describe. And it can also help us explain something that might be overly abstract but already done statistically. There's ways that we can use visualizations to help us appreciate a point that might otherwise be quite abstract. In fact, we're going to see that here later with trend lines, where I think regression tables and regression formula can be a bit abstract, but by pairing it with a visualization, it can help make sense of it. And now just FYI, that's the Matplotlib gallery. It's over there. And you can see all kinds of different sort of examples of code and stuff. And just look at these, each one the plotting categorical or whatever. Now if we click on one, you'll notice here that it also shows all the code. So you can test this out for yourself and toy around with the visualization types. So now in order to get some data for visualization, you'll see in that gallery, as well as in the book, examples of distribution generators. Now a generator is a formula that will create some number, and that number should fall within some set of numbers, which we'd call a distribution, and the pattern of that distribution is normally defined by the algorithm in some important way. So the way we went, so the simplest one would be a uniform distribution, and that's like pretty much every number is equally likely, and it doesn't mean that you're going to get exactly the same value or the same count of numbers. So because each time it's going to randomly generate a number, well, close enough to random for our work here. It's going to randomly generate a number, and then the next time it's going to generate a number again, and it's going to keep doing that. So it doesn't, if you generate 16 numbers, you're not guaranteed to get 1, 2, and 1, 7, and 1, 13, and 1, 10. You might get a couple 2s, and you might not see a 10. You might get a 3 8s and not see a 13 or a 14. So the thing is that you with this distribution, with a distributional generator, you get this nice sort of bit of noise going on. But the expected value, we should be able to have one. So the thing is, I did a distribution here of random numbers, and I made the size equal to 8,000. And I said that high and low is 0 and 16, so we have 16 possible buckets. So 8,000 divided by 16 is 500. So we should see about 500 in each bucket, and that's what we do. We don't see exactly 500, but we see about 500 right here. So now the thing about this uniform distribution is that it means that if we know how many number threes there are, or how many twos there are, let's say this is 0, 1, 2, it shouldn't really help us make a better guess of these other numbers, other than knowing the expected value. In this case, the expected value is 500. 8,000 of them, so we're going to expect 500 in each bucket. But now, if we look at this value, it's really low, or this value is high. Is it going to tell us something additional about that? Not really. That's just it. It's a uniform distribution. Okay, so now I make that claim, but we might want to test that statistically. So first, let's have a look at how we generate that number, and then we'll come back and have a look at that. Okay, so first off, well, we see this later on, but I want to render it here now. This is 3 different distributions, and here's a uniform, a normal, and an exponential. It's this sort of gaps in here partially come because of the way it is binned, and the binning is like chunking these distributions into small and perceivable groups. Even if the actual numbers, there may be many, many, many little numbers within them, they just kind of group them in. And so here's the one that we were looking at there today, and you'll notice that I have this seed here, the seed that says 1, 2, 3, 4, 5, 6. That means that that's the random number generator. It's a deterministic random number generator, so it's going to calculate the same set of random numbers every time. So why is it really random then? Well, interestingly, where the randomness comes from the seed as well. We don't normally you have the choice. Well, say you have the choice of either letting Python choose the seed, and in which case it'll take some random, what it believes is close as possible to a random number, maybe something from the clock, the time, and then it'll use that to calculate the random number. So actually, if you see this, if we just run this again, watch how these numbers are going to change. And similarly, if we could do whatever, and they change. So every time, every seed will give slightly different numbers, but the seed itself, once we use that, because it's a deterministic algorithm, it'll give the same numbers every time. Now, I did that in the book because I wanted to select a distribution that had some features that I thought made it look like tidy and worth it, because some are a little more noisy than others. And in this case, we're using this seed right here, and here's our 16 values. Okay, so what I did then was actually, there's not 16 values, there's 8,000 of them, but I used a value count statement. I took that series, made a distribution, and then the value counts produces the, 500, around 500 ones, 500 twos, 500 threes, and so forth and so forth. Okay, so then this is our distribution right here. Okay, so we're going to then plot that, and this is how we did it right here. You'll notice I use Seaborn this time. I use SNS. It's for Seaborn, and did a hist plot. And here's the number of bins. I think it's quite tidy looking. And right there we can see there's actually 16 of them, so we can count each one of them. Notice if you make the bins different, it'll try to chunk them up, but because there's 16 numbers, trying to put it into 10 different bins is not going to work correctly. Like, just watch me put it into 8 bins, it'll be quite tidy. There we go. But 10 bins, well, we're going to have the maybe number 0 is in one bin, 2 is in another, 3 and 4, 5, 6 and 7, 8, 9 and 10, 11. See, so that doesn't really work very well. So you got to be careful with how you bin your numbers so that you don't get these sort of statistical artifacts right here. Okay, so we noticed this here, and we said it's a uniform value. So knowing some value for 5 is not going to really inform us about the value for 6 or 7 any more than the expected value. But is that true? Well, we can use a chi-squared test for that. Now, a chi-squared test is really popular in statistical work, and it's a relatively simple test. We're not going to get too much into the mechanics of it here, but we can say that you can give it a set of cells, and it doesn't have to be just like 1, 2, 3, 4, 5, 6. It can be a table, a rectangle of cells, and it'll assume, based on the count, that each cell should have an equal number. So in this case, it should say each cell should have 500. If there's kind of a deviation from that. If there's something unexpected, so that there's one value that's a little more than we would have in that count, or one value is a little less, then the chi-squared test is often going to show that using a p-value. So chi-squared is really useful for telling us that there's something different than what we expect. Now, it's pretty limited otherwise. It can't tell us much more than that. It's not going to tell us the strength or the direction or whether there's a trend, but it can tell us whether there's some sort of difference worth looking for. In this case, there's not. The p-value is 0.9, which means 90 times out of 100, we can expect to see a distribution like this just by chance. And that way the chi-squared is tolerant of the fact that all the numbers don't have to be right on the line at 500. They can be a little bit above, a little bit below, but it's not really much different from chance in the sum total of it. Now, imagine if we take some from one bucket, scoop it out of one bucket, and pour it into another bucket. So we'll take 90 from this bucket right here of 7, or sorry, we'll take 90 from this bucket of, I think it's 13, and give it to 7. So now, notice that the axis is going to change. Now our range is going from 425 to 475 in order to accommodate this dot up here and this dot down there. See, we took 90 from 13 and we gave it to 7. So look, it's pretty high now, and this one's also pretty low. But because we took it and gave it to the other, when you sum them all up and average, the average should still be 500. So we still have the same expected value, but now the chi-squared's picked up something. It's suggested that actually it seems like there's some values here that are not what we would expect. It's not going to give us any more detail than that, but it is going to give us something to pursue there, that the values are not quite even. Okay, so we can have a look at that in JupyterLab as well. Notice in Jupyter I don't plot this first one right here. It's a bit redundant, but I do plot the second. Now there's a number of different packages for doing statistics in Python. Pandas just by itself has some statistical facilities. You know, skewness is available there, and mean, and so forth. There's also sklearn, which is pretty sophisticated, and of course the more machine learning packages. But SciPy here is a pretty lightweight one, and I like its chi-square method because it returns right here a tuple, and so we can have right there a chi-squared value and the p-value. Now, so we didn't print the chi-square, we can, but that value isn't going to make a lot of sense unless you look it up on a chi-squared table in order to get the p-value. P-value of this, and the expected value is 500. Okay, very good. So we can see that the p-value is really high. We would definitely expect to see this if there's no relation between the values. It doesn't seem like we're going to get any information from that. Now, on the other hand, let's see, and yeah, see, there's the expected value. On the other hand, if we look, we're going to copy that table, and then in this new table, I'm going to take 7, and I'm going to add 90, and then for 13, we're going to take 90 away. So the expected value should be the same, but the value should vary. And then we look at that. We see down here our chart, and then the p-value. Now, of course, I'll print the chi-square here as well. Okay, yes. In this case, the value is much larger. You'd have to look up that value on a table in some manner to really get a sense of the p-value. But here, sure enough, indeed, the p-value is much lower. Much lower. It's really not likely that given this expected value, we're going to see a distribution like this by chance. It'd be really surprising to see values this extreme. So what if we only have one value this extreme, or so forth? You know, you can play around with that yourself, but we can definitely tell that there's something here that this is not a uniform distribution. And if you had a random number generator that produced this many 7s and this few 13s relative to the rest of the numbers, you're gonna have a random number generator that does something funny. It's probably biased in some way. Okay, so we know that the uniform distribution, that each of the buckets, well, they're around 500 there, right? But now, what if we put a trend line through those numbers? Now, this isn't the one where we borrowed the 90 and gave it to the other. This is the original one. So imagine we have this one here, We put a trend line. Look, what's happening with the trend line? It looks like it's going down. Maybe it means that lower numbers are more likely, higher numbers are less likely. That seems to be what a trend line is showing. So maybe our random number generator is busted. Maybe we shouldn't use it. Is that really the case? Well, things that we can use a regression table to get a sense of this. But we can actually kind of cut to the chase here a little bit. You'll notice in behind this trend line, this gray shading or this lighter blue shading, and this is the confidence interval. And so the thing is that while there is a trend line going down, the confidence interval is really wide. What do we mean by it's really wide? Imagine you could actually draw a line that starts up here above 500 and goes down below, or vice versa. So you could draw a line where the slope of that line is actually opposite of what we see here, and it would still be within the confidence interval. So the confidence interval is so wide we're not really sure what's going on with that. Why is it so wide? Well, that's because what the regression does in making this line, it tries to find the line of best fit. But you'll notice that even though there's a line of best fit, there's lots of values that are pretty far from that line. And so these are the predictions for each value, and this is the observations right here. So the observations, there's a difference between the observations and the predicted, and that difference is pretty wide. Because that difference is pretty wide, that means we can't be confident that the line is going up or that the line is going down. So you see here, in a regression, we I haven't put the formula up here. I have shown it in the book. It's pretty common, y equals a plus bx or something like that. And the idea is that there's an intercept. There's when the trend line is at 0, what's the value? And that we normally treat as like our expected value. And it says here, when x is 0, y is predicted to be 505, so it's pretty close to our expected value. And when x is 0, 95% of the time it's predicted to be within 488 to 523. So actually it's pretty wide, but nevertheless it's pretty certain that it's around our expected value. And so that's good. If we actually did this in a model where we looked for p-values, it would show that the intercept is significant. On the other hand, the slope of this trend line, the fact that it's going down here, now that's because, well, when x increases a unit, it says the slope is going to be minus 0.8. So we see that, and it keeps going down by 1, by 1, by 1, by 1. And by the time from here, we get down to here. Okay, so that's the slope. It's negative, and that makes sense. And it says when x increases by 1 unit, 95% of the time, y is predicted to increase by somewhere between minus 2.7 and 1.2. Okay, so that's not very good. What that means is that y is predicted to increase by maybe a positive number, maybe a negative number. Okay, so because y is predicted to either maybe go up or go down, we're not really sure that y is going to go up or go down at all. And so while we have this original trend line right here through this observation, it's not statistically significant. We shouldn't be confident in that trend line. Okay, so we can see that down here. Let's have a look. Here's our trend line. Somehow I feel like I've generated a different plot here. But it's also possible the random number generator is updated in some way. Nope, there we are. There we go, that's better. Okay, so here we are. Here's our trend line. You'll notice this time instead of a scatter plot, we used a reg plot. That's a regression plot. So that means it takes does the scatter plot, but it also does regression trend line type things in it. Now, within that, you'll notice that there are some keywords for the line plot or some keywords for the scatter plot that you can send through Seaborn. And that's what I've done here with this line underscore KWS. And these are arguments for one of the subplots. Now you can have a look at that in the Seaborn documentation, but it should, hopefully that will help clarify how we manage that. You'll also notice that I put label in here, and when I put label, it says observed counts, then it's going to show up in this legend. Down here, I have a label expected trends, and similarly, that shows up in the legend as well. And of course, that's why we did this label inside the line so that we can have the trend line within there. I guess we have this. It looks like regression. It's going down. Confidence interval is really wide. And so now let's have a look at that regression itself. This time I'm going to use a different stats program. I'm going to use stats models. You'll notice that it's giving me a warning. It's not really a relevant warning, to be honest. And you'll notice even if you run it a second time, it doesn't show it. Okay, so here we are. It ran the regression, did those things that build the model, and then the predicted values are actually the values that would be on this trend line. So I use those predicted values to draw little vertical lines from the observed counts to where it's predicted. Pretty neat. And then here's how we did the that sentence there, which said when x is this and y is that. When you have a model, a regression model here, in this case we have the output is EST, or the estimates, and so then from the estimates you can query it. It's its own object. And so one way that you can do or query is ask for the confidence intervals. And so the confidence intervals, if you follow what I've put in these F insertions, that tells you how we've been able to use the regression object and then put it in a sentence to make sense. Now, down below, we'll show how to do that in a table as well. And traditionally, you might see a regression in a table, but I wanted to show here different important components because I think that they're the real important components for helping to build the story of what we're showing in here, rather than just showing. You can get a lot of data. Let's sort of cherry pick the different numbers as we want. Test this with some empirical data. I was able to find kind of an interesting little data set. This is from the Office of National Statistics, and it shows the average number of births per year over a 20-year period in the UK. The URL for the direct article in the dataset is in the book, and the data, because it's publicly available, is also available on the GitHub archive. Okay, so you can see what we have here. The data has numbers from 0 to 365. We can plot that, and then we can see the average number of births per day. And we kind of can make some sense out of it right here. Now, there's not really enough detail here to tell what might be a useful story, but we can still see something. We got some numbers that are really low down here, which is really quite peculiar, interesting relative to the rest of them. We got this peak that's happening over here, and then we have this line that's going up, and you'll notice compared to the last one where we had like our expected value, and then we had the trend line, but the confidence interval was really big. In this case, the confidence interval is kind of small. It's actually showing that it doesn't cross 0 on this side here, so it might think that it's really trending upwards. Now, it's worth noting that because this is an average per year, if we keep extrapolating, it's not going to keep going up to the next year and then the next year. That's not how it works. So what we're showing here is just like the first intuition. What we would probably want to do if we're actually doing a more robust analysis of this would be something like an ARIMA model, which does this, but it kind of takes into account the fact that the time periods would be cyclical and in a way that can let us know whether there's like some sort of seasonality in the data. But for here, it's just some tidy data, and one where we can still tell a quantitative story about what's happening with regards to babies. Okay, so this time you'll notice I've actually put the regression in a table. Now, this table's pretty neat. This came from a package called Stargazer. It was originally in R. It now is in Python, and it just formats a regression table in a nice way, in a way that one might expect in an academic paper. Whereas the standard output from the stats models regression gives lots of data and gives it in like a monospace format, and it's not really ideal. Okay, so we can see here, we got some stars as well, and those are for the p-values. And so, once again, that suggests, in this case, that the model is pretty confident, both in the constant and in this x1 right here. And x1 is the days. So it's I mean, probably should have labeled that something better. But we can see here it's just the days. As each day goes up, the number of births increases by 0.13 over the course of the year. Now, it's a really simple model. Like I said, a REMA would do better. Even a curve might do better than that. But nevertheless, it can show us right here this kind of tight confidence interval. Now, we do have some sense there's some seasonality in this, and I have some intuitions about this, but it's not quite obvious from this data right here. So first we're going to have a look at how we rendered this data and this regression, and then we'll try to drill into that story a little bit. Okay, so going over here to Firefox, you can see we have our data. The average number of births per day was 1813. So now the intercept here, why wasn't that 1813? Because actually it was more like, well, you take 1813 somewhere around here as the expected value, and if we keep adding that 0.13 over the course of the year, the expected value should show up somewhere in the middle of this. Okay, so let's see what the data looks like. It kind of looks like this, 1st of January, and then here's the average, and so forth. So the index 0 through 365, really simple, and then the average, we can pop that in, put it into a data frame. You can see here index and average, and then show that regression plot, just like what we've done here. We've got a horizontal line for the mean as well, and gave it a dotted line. So there we have that, and let's see, we can do our stats models. And now you can see I'm gonna show the default Python output here when we do this. And here's what I said. It's like really monospace. It's big. It's got lots of details. They're kind of useful. It sets this up. We can see our constant starts at around 1790 and then kind of ticks up as it goes along. Here's how much it ticks up by, and here's how confident the model is. You'll notice that in both cases, it's on either side of 0. That's what we want. So we know either it's sure that there's some intercept, and it's sure that it's either trending upwards or trending downwards. And some of these others are really important, or not. Well, they're really useful. One that people often pay attention to is the R-squared value, which is it's a PRE statistic, or a proportional reduction in error statistic. So knowing which day of the year it is, we can get about a 5% better guess than random of knowing what the number of births is on that day. Now that's not, of course, distributed evenly throughout the year because we have this really noisy, wavy trend. Okay, so now here's how we would use Stargazer for this, so I've installed it. You can install it using pip, and compared to that other model, here's what it looks like in Stargazer. So much more tidy and much more like an academic model. And Stargazer kind of is quite flexible for things like nested models. So often we would do this, but then we'd have another model where we have this plus an extra variable. And Stargazer will make that quite tidy. This is render HTML, but if you render LaTeX, then you get something that looks like this. Now, that right there is not going to be very clear as a table right now, but if you put it into a LaTeX file, it'll make it look like a nice tidy table that looks something like what I've shown on the PowerPoint. Okay, so now I'd like to actually say, well, maybe we can have a sense of this. Let's drill in a little further. So this down right here, let's say the Christmas holidays are probably pretty relevant. It's a time that a lot of people get away from work. Not everyone does, but a lot of people do, and particularly in that interval between Christmas and New Year's, get some time to themselves and their partners and so forth. And so, well, one thing people seem to be able to do is avoid giving birth on Christmas or on Boxing Day. Now, not everyone can avoid giving birth, and not every birth can be a delay, but there is some means to delay that, especially if it's by operation, like a cesarean or induced or something. And so that really shows up in the data with this, with these outliers right here, where people just don't want to have their kids on Christmas Day. I guess get half the gifts or something. But anyway, so that's with respect to having births, and that'll show us what we have here is an outlier. And we also have this sort of like trend line, but I think the trend line has actually been hauled up a little bit. It's got some extra leverage over the course of the year when we think about Christmas holidays and then 9 months later. So I looked up, and what are the what is exactly the average length of a pregnancy, and the standard deviations for that pregnancy from some calculations from a medical journal. And so it turns out that the 95% range is about 20 days on either side, so it's a 40-day interval. So I marked that around Christmas, and actually the peak happens a little bit after, so it does kind of have a sense that well, some people like to get especially cozy over the Christmas holidays, and that does tend to show up in the data. Perhaps having levering up the trend, but also with respect to having children, people are a bit hesitant on Christmas, and so that shows outliers in that. So all this is marked in here, and compared to the last one, here's some things that we've done. First of all, I set some X and Y labels here. These are really useful, and you generally will want to have that there. But in the case where you have really nice, clear X ticks, it may or may not be necessary to fully also have a label, but I did want to put it there just to show it. And I have these usable axes ticks there. I did this with M dates, which is a part of the dates library, and then the month locator. And so then you go down and you see right here, it goes right up until, and I put January at the end. You can kind of fiddle with that in a way to like check the range so that you only get right up to December, but I think that's fine. We have a legend, and you'll notice that I discussed that earlier by saying we add a label to something. So I added a label in the code, and then by adding a label for each of these things, they show up in the legend. I had vertical bars showing key markers, both this dotted one, and then also this confidence interval as kind of a band. This is we've also seen confidence intervals before, and I do think they're generally useful because we don't want to have the expected value give us too much of an expectation if the data is a bit noisy. I also have what I've described here as only in the slides as occlusion aware, occlusion aware glyphs. And so by that I'm referring to the fact that these glyphs right here have a little bit of transparency on them. So you get to see where, when there's two of them nearby, that they're really on top of each other. And that's because if we say used circles and they were flat and they weren't transparent, you may have a lot of overlap between them, and then you don't really get a sense of the density of the dots there. And that density can actually be really useful to give us a sense that right here it's a bit noisy, but here there's definitely like more dense. And then finally just some annotations, and I did this down here. I put in this date. I did that myself, like by hand, we say, by selecting the right X and Y coordinates, and I just did that using plot.txt. So all of this, I think, tells a story about how there it does seem to be a pretty uniform distribution of births throughout the year, but there is a handful of times during the year that that then lead to some either some trends or some outliers. And I did say I was going to do that in Jupyter, so I will tick over to that really quickly. I don't want to spend too much time on it. It's a big piece of code, and I would encourage you to review it for yourself. But you'll see here, well, first we take that plot object, we get our figure and an axis. We only have one figure, so we only use one axis. And then we do these things, add the date locators, and here's some parameters. And this is where I got those parameters from for like the for the range, for the confidence interval. 9 months later equals this. And so forth. And so there's a lot that's really going into this chart, but each thing that goes into it is quite deliberate, as it's meant to help us give some insight into this. Now we run this, and here we have the chart at the end. And once again, of course, because it's an SVG, it's nice and clear, so we can zoom in and see all those little pluses there instead of making it kind of blurry and fuzzy. Okay, so I want to show here for a little bit. We only saw one graphic. I mean, I did show this really briefly at the beginning, but let's have a look at it again. And I want to show that how matplotlib arranges figures. You'll see here that you can do the plot object. You can generate subplots, and in this case, I did a 1 by 3. So that's 1 row, 3 columns, and here's the size of the figure, and that size is just some number that, or some ratio that's relevant for JupyterLab. So we do that, and then it always returns this figure object, and then instead of returning just one AX like we've seen, I suppose we've seen on the Firefox up here, x, and there's just one subplot, and you can make use of these two objects right here. In this case, we have 3 of them. Now, each one of those objects, AX1, AX2, AX3, those names are by convention. I just came up with them. But you'll notice that then when we do our plots, we assign them to each of these little cells. And so that's why histplot shows up for the uniform here, and then the normal distribution here, and then the exponential distribution right here. And you can see that each of these, a uniform doesn't really have a peak, or it really shouldn't have a peak. A normal distribution has one peak, as does an exponential. Sometimes we can have bimodal distributions where there might be multiple peaks going on. It's also worth noting that our distributions can come from continuous or discrete generators. And an exponential generator here, this is a continuous generator. But you can do something like a Poisson distribution, which is a distribution of like repeated odds of something happening, and because it's repeated odds, it's count data, and so it similarly has like most of the time it never happens, but sometimes it happens. And if it happens to some people, it seems to happen to them a lot, and that's a Poisson. But so it'll look kind of like an exponential, but it has some different features to it. So you might want to be careful with that. Now, it's interestingly that for some distributions, the expected value is really important. So for example, for a uniform, we get as expected value, I guess whatever this was, around 90 or something. Depends on the bins. And then everything would be kind of around that expected value. Now, a normal distribution, whatever our expected value is, in this case it's 0, that's the most common value, and then they decrease on either side, and they decrease at an increasing rate. So that's why it kind of has this, like, I keep hitting this mic, sorry. And that's why it has this, really kind of steepness, but the steepness levels off from our perspective, but things just keep getting increasingly less common, or less likely to be observed in a normal distribution. In an exponential distribution, we can see here that most of the values cluster near the lower rates, and then very rarely, but indeed, do we see values that are very extreme. And that might be something like chat frequency with people. Most you'd get a number that's similar to this, where some people you talk to a lot, maybe send even 200 messages per month or even per week. And for some people, you might send a message or two, but you still care about them or whatever. But it's they're weaker ties, and they just don't get the same sort of contact. So matplotlib shows us how to have multiple figures in the same plot. Mention that, and there's some baseline distributions. Now, while a single distribution is useful, and it's important to know its shape and have a sense of that when you're trying to do some sort of statistical test, joint distributions, or jointly comparing them, I think really gets us more where we want to go. So the key difference in the joint comparison of distributions is whether the data is categorical or whether it's numeric. And one might say whether it's orderable or not orderable. There's a lot of other kinds of distinctions, and different texts will accentuate different ones, such as Stevens' notions of like ratio, interval, and ordinal, which I cover in the book, or whether something is an integer or a float. I think it's less relevant to have an encyclopedic sense of those distinctions than to ask some key questions about the data. So, for example, is the data really skewed? And if it's skewed, should we then use a non-parametric measure rather than a parametric one? So a non-parametric measure will calculate things by rank order. So this is the first lowest value, the second lowest value, and keeps going up till it gets the highest value. It goes 0 to n. And then it does a correlation with those rank orders. Whereas a parametric test really cares about the value. So this might be, you might have a distribution that has a 1, another 1, a 3, a 5, a 20, a 500. I mean, that 500 is much higher than the others. In a correlation, in a parametric correlation, that'll make a difference. It'll really it'll pull all the other numbers towards it. Whereas in a non-parametric, it's just like these two are the same low rank order, then this is the next rank order, and it'll only go from 0, 1, 2, 3, 4. Does the data represent measurably fixed categories like count data, or relative measurements like ordinal data? So while we have a sense that strongly disagree, it might be lower than disagree might be lower than agree, might be lower than strongly agree. So we have an ordered ranking. People don't necessarily feel the difference between agree and strongly disagree the same way they do the difference between agree and disagree. So it's only it's the next category up, so in the ordinal scale. But does that mean that the width is interpreted as equal? It may or may not. So that's a question we're going to want to care about for this, and also help us understand whether we should once again consider parametric or non-parametric. Is the data meaningfully divisible is also another one. So I do remember this old sort of funny newspaper cartoon. You go into someone's house and they say saw a child there, and then there was another child, and it was kind of like almost like kind of like cross section. It didn't look like blood and guts. It was just like a weird sort of cartoony type thing. And of course, this is me and my wife and our average 1.5 children. And because the notion was that on average people were having, I guess at the time, 1.5, 1.6 children, and nobody actually has 0.6 of a child. So it's not really meaningfully divisible. It's count data. But on the other hand, time we do think of as meaningfully divisible. We can always get a slightly smaller unit of time. And so 1.5 hours makes more sense than 1.5 children, at least in the concrete rather than in the abstract. And you might want to make a consideration of whether the data you have, the distributions you have, whether they represent repeated measures or independent measures. So, for example, if we want to compare the mean value of two different distributions, it matters whether those distributions are a series of people in an experiment at time 1, and then the same people in another experiment at time 2, or whether it's a series of people for one experiment and then a different series of people for the second experiment. So that's a key consideration with two distributions as well. Okay, well, while these things can often matter for the display of a single distribution, they're especially important for joint distributions because the tests will make assumptions based on these things. If you have repeated measures, it's a different t-test than independent measures. If you have count data that you can divide versus or that you can't divide versus that you can, that will make a difference to the test. Oftentimes, if you forget the test itself, you can look up based on the specifics of your data, and people will advise in various books and online which test is entailed by the shape of your data. Okay, so but ultimately most of what we want to do is to make things mutually informative. So that means if we learn something about one distribution, it's going to help us understand something about the other distribution. And that doesn't have to be symmetric. Learning, well, I'll just leave it at there. It doesn't have to be symmetric. So with two continuous measures, if they're nearly normally distributed, you'd use a correlation, for example, to see if learning about one will give us some information about the other. If it's highly skewed, you might use a Mann-Whitney U-test, which is like a correlation except with the rank order of the variable, so it makes it non-parametric. With one continuous, one categorical measure, we often will facet the data by the categorical measure. So you might have hours spent on watching TV, and that would be a continuous measure. Time, remember, we think is quite divisible. And then we might have hours watching TV, but we have it for one group of people and then another group of people, or maybe weekday versus weekend. So we have a series of people, and there's their weekend value versus their weekday value. What we're doing is we tend to split the continuous distribution and look at that within facets of the categories. Then those different facets, they're each their own distribution, and we compare the differences in their means and how sort of spread out and noisy the distribution is, how much dispersion it has. And we can do that on a t-test for between two values, so one and another, the mean comparison between them. Or if we have multiple distributions, maybe it's not weekday or weekend, maybe we're comparing average TV watching in one country versus another country versus a third country and a fourth country, etc. So the analysis of variance test, ANOVA, will compare the means of all those different countries on this distribution. So with two categorical measures, we might do a chi-squared. So we'll have a table, and we'll have a table of one value and a table of another value. So what's your favorite color, and what country are you from? So we wouldn't really rank order the colors. Maybe you could put them on a spectrum, but I don't really think that that's the point here. We just say they're separate colors. And then each of the countries, similarly, we're not going to order them. And so we would just expect, if there's no relation between country and favorite color, that it's going to be an even number of countries per color, or an even number of colors per country. That's not going to be biased in some way. But if it happens that people from, I don't know, from America are particularly biased towards liking red, white, and or blue, then that would show up in the data. Now, we wouldn't necessarily know a direction there. We're not looking for some sort of trend through the data. We're just looking for some values being more than we would expect, or less than we would expect, just evenly by chance. So we consider those associations visually. Now, for two continuous, here's an example. I use a heat map, and the heat map shows the density. You could also do a scatter plot. This particular plot's kind of neat because it also shows the each individual distribution on the sides here, as well as the values. Now, you'll notice when I'm referring to mutually informative, these were two independently generated distributions. This one is log normal, so it's a bit skewed. So a bit of it comes some outliers, but most of the data is around here. And this one's just a normal, so most of the data is around the midpoint. As it happens, this is just a blob here. That blob doesn't seem to be like have a shape other than just like it's a general blobbiness. So the most common values are in the middle of here and the middle of here. So we're not really getting a lot of mutual information, even if we can see the two of them together. If we were to see clusters or a shape that has like a direction, then indeed the distribution from one may help us inform the other distribution. Now, with categorical stuff, we can facet. Like I was suggesting earlier, in this case, we can look at the different flowers. And these are species of flowers. It's a really neat old data set, and I'll be showing it now again in a minute. So with two categorical variables, we'd use tables like I was describing, and we can make use of a third variable. And so the species here is a facet. And so this facet, we're going to use that as different colors. Now, this is just two distributions, one distribution per flower, but you can do a scatter plot here, and you could make each of the flowers a different color, for example. And so that's indeed what we can do here with this pair grid. A pair grid's a really neat sort of visualization. It's a bit dense to produce, and you can set a number of options for the upper diagonal and the lower diagonal. In the upper diagonal right here, we can see it's a scatter plot. In the bottom, it's a KDE plot. And that means kernel density estimate. And so it gives us kind of this sense of, for the most part, this Virginica their petal length shows up within this range, and their petal width shows up within this range. So you kind of see that that's one blob for them. Whereas Setosa, they would have smaller petal lengths and smaller petal widths, little tiny flower petals. And so they mainly show up down here at the bottom. We can see the actual observations that were used to produce this KDE plot right here. And on the diagonal, because it's sepal length by sepal length, it just shows the distribution. Now, because we've faceted it by the three flowers, we can show the X and Y and by color here. So we're really getting a lot of information in this one. So now each of the charts reveals a different potential insight about the flowers, but I want to particularly notice sepal width and petal length. Look at this one right here. Now, compared to this, petal length and petal width, it seems like pretty linear. Longer petals, wider petals. But now the sepal, in case you're wondering, the sepal is like this green part before the flower, the nice colory flower bit. It would seem that for Virginica and versicolor, there's a bit of a relationship with the wider, longer. But look at this Setosa flower. It has lots of wide petals and lots of narrow petals. It doesn't really seem to be too related with the petal length. So it seems like we have some relationships on a per flower basis, where we might have some other relationships right here that are just for all of that flower, all the different species, or within the same sort of genus, whatever it is, just above the species. They're all otherwise very similar flowers. Okay, so I want to show us very quickly how we might have a look at that. And let's go down here, and we're going to get to the pair grid. So we're going to load the data set. It comes with Seaborn by default, so you can just load data set. We don't have to find it anywhere. And we have a sense. You'll notice I sampled within here, and by sampling, we're not getting the first or the last data points, just any old 6. Here's a KDE plot of sepal width. So this is what we showed earlier, and it's just the KDE plot for one distribution is kind of like a histogram. It's just how many are at any given point, and most of the density, it's most commonly within the sepal width. Okay, so now we can look at that pair grid. You'll see what I've got for upper and lower. I do different plots. For the diagonal, I do a different plot. You can set all those things, add a legend. This will take a couple seconds to run. Oh, there, look at that. And once again, this is something that really benefits from having the SVG or the PDF rather than rasterized. Okay, so now let's drill into that data a little bit. So I want to think in terms of the elaboration model. That's how we use a third variable here. So we have things like sepal width and petal length and whatever, all these nice measurements, and we have this third variable, the kind of flower. So maybe we can make use of that to make some claims or explore the data. Okay, so given a relationship between x and y, such as sepal width and petal length, what happens when you take into account a third variable, in this case, the type of flower? So if z correlates with both x and y, and accounting for this eliminates the relationship between x and y, then the original relationship was spurious. So in the book, in the prior chapter, I talked about circuses and a circus being more popular in southern North America, and if it is, then we might assume ethnicity will be correlated with circus, but then actually it's not. It's weather. It's the fact that it's sunnier and people like going to fairs and things when it's sunny. So the weather was correlating both with where some people live as well as the likelihood of people going to a circus. So that's a spurious association. Now, interestingly, if you add a third variable and it makes a relationship clearer, then you have a suppressive relationship. And you don't really see that very often, but we do see that here in the data. It's kind of neat, so we're going to show it on the next slides, one of the last things we do. So if Z does not alter the relationship but correlates with them, then it's more robust. So let's say the relationship between x and y has some sort of value, and that value, you control for a third variable, and that value still persists. Then we would think that that relationship is more robust, and we haven't proven that relationship, but we have replicated it in the presence of some other variable. Now, the reason that we have to say it has to correlate with, one or the other values is because if it doesn't correlate with either x or y, then sure, we just throw anything in there and say, look, I've replicated the relationship, but you haven't really ensured that your model has any sophistication. You've just thrown in some random data and shown that it was random. Now, if it only holds for some classes of this but not the others, so maybe we have a correlation in some flower types but not other flower types, well, that's called specification. And there's some other variations of this. I mentioned that this is in Babby's book, The Practice of Social Research. I believe the original elaboration model came from Lazarsfeld, a really relevant and interesting social scientist. But now let's have a look at that in our data. And we noticed that there was some funny stuff going on here with sepal width. See how these blobs are kind of separate from these other ones compared to the rest. If you look at this as a heat map instead of as a as that pair grid, we can see here that there's petal length and sepal length really well correlated, petal length, petal width really well correlated, but these sepal widths are negatively correlated. So does that mean as the flower gets larger, the plant parts of the plant get smaller? That doesn't really make any sense, but kind of how it would suggest here. So let's see, the pair plot shows that actually it seems like there's 3 different clusters, that they cluster as much as anything else. This is not so much a trend, but perhaps a classification. Okay, so why would that be relevant? We'll just have a look now when we cluster this. if we take this correlation, this one right here, petal length and sepal width, right there, if you draw a trend line through that, you're going to get this, you're going to get a real negative slope, but it's also going to be artificial. And so if we actually go per species instead, we look at Setosa and the correlation is, it's positive, but it's not very significant. You can see, you can kind of see that down here, that it's like as the sepal width increases, the petal length also increases, but it's not really that remarkable. And in fact, it's not even statistically significant. But on the other hand, for the other two species, for versicolor and virginica, you can see that there is this nice, clear, obvious linear trend where larger or longer petals, longer flower petals, wider sepals. So, I mean, it's, it's just flowers, not the most exciting, but I think what's really interesting for me is that we can actually see out in empirical work how putting multiple clusters or classifications, different classes of things in the same distribution can make a difference and can actually even give us a kind of an obscured value that when we then subset that, and when we elaborate that value, that can reveal some new insights or new data. The other reason why I like this particular example is because it's pretty tidy. It has stuff that you can download from Seaborn, and it shows how you can use visualization and statistical analysis in concert. That we're not saying that this is going to prove things for us, and we're not saying we're not going to trust this just because it has a formula. We're going to kind of oscillate back and forth between them and use our intuitions from one to help explain the other, and in doing so get a fuller picture of the relationship between the variables. So I say that's in Jupyter, but the code is in there, and I think I'll leave it for you to run because it really just shows that. So I just want to summarize. Expectations and observations, they work together to help create insight. We have expectations from past literature. We integrate that into our thoughts, into our ideas. It gives us intuitions. We structure that in some way in a data collection effort. And we see observations. We get patterns out of them. That can be presented in a tabular way, a statistical way, or a visual way. Now, different presentations have different goals. Usually visualization gives us an intuition of the shape of a distribution, and statistics help us to determine whether that shape could have occurred by chance. Now, we can test for unexpected distributions using a chi-square test, but this will not really give us a strength or a direction, only the presence of some value that deviates far from the expected value. Further tests like regressions can help us understand trends. Now we can do this for joint distributions and look at correlations among more complex tasks. I alluded to things here like in ANOVA, but we really didn't cover that. Instead, it's just the basic, how do we use visualizations and some stats together? But indeed, this does stretch and gets increasingly sophisticated as you encounter more and more statistics. So using an approach like the elaboration model helps whet our appetite for that by showing how a third variable is not just to help minimize uncertainty. It's not just out there to increase in our squared. It's a logic that we can use to elaborate on the relationship between any two variables. And I think that's really a useful way to talk about this. That what we're doing is trying to use data to perform some form of reasoning, not just to make something aesthetically engaging. So now just some questions and extensions based on this. So not all data looks great on a linear axis. We've shown everything here on a linear axis, so it's always like 1, 2, 3, 4, 5, or January, February, March. But some things look better on a logarithmic axis, where a linear increase in distance on the picture means a change in an order of magnitude. And so we're going from 1 to 10 to 100 to 1,000, and that's just all within within each one step. So now some distributions that are really skewed, they'll look better on a log scale. So here's some questions. Does it work better to make both x and y log? And what about for a power distribution? Now, power distribution is kind of a special distribution, and if you get it right when you create that distribution and then show it on a log scale or a log plot, it should actually look like a straight line. And that has some really neat properties, and you hear a lot about those properties in the network analysis and in the thing called scale-free graphs. Just have an explore of that. See how it looks in a linear scale. It might not make any sense. And then on a log scale, it's like, oh, okay, I get it now. Now try to take a distribution of data from one of the previous chapters, such as distribution of upvotes on Reddit. I mean, we were a bit slack on the aesthetics. We would just say, here's the histogram. But now, this time, try to do a little better. Try to tell a story over time. Now, it might just be all the stories in the past few hours if you're only doing a Reddit pull by recency. But then, maybe tell a story. Was there a time of the day when stories were especially popular? Did the stories talk about one thing earlier in the day and one thing else later in the day? This is less now about the statistics per se, but like, can you wrangle data so you can present it and tell a story, annotate a chart? Now, we've only scratched the surface of statistical estimation here, particularly within regression, which is so light compared to what's available. But the best, I think one of the most effective ways forward is to now think about multivariate regression. What happens when you add multiple variables? And then after that, you should probably have investigate things like diagnostics. But starting with multiple regression, go take one of those Reddit tables, something maybe like you have data.ups for the upvotes, and a second number. And it might be the time, so how long it's been since the story was posted, or it might be the length of the title. Do we think that longer titles get more upvotes? When you're adding both of those things into a regression, then you're starting to account for multiple features together. Have a look at that, see if you can tell a story about the joint influence of these two things. Now that story will be very local. It'll only be to that data. That's not to say that'll prove how things work on Reddit. How they justify or how they generalize outwards from that is its own delicate art that extends beyond this book. But we'll get there, we'll start to get there by being able to consider models where we jointly include lots of different features. So we didn't get a lot of data to do that so far. A Reddit distribution here, a Twitter distribution there. But to really wring out a lot of insight from data, we should probably get a bigger data set. So the next chapter, we're going to start on this silo chapters. We're going to look at Stack Exchange, and a particular Stack Exchange called the Movie Stack Exchange. And that's because it's of a reasonable size and it's really interesting. But it's like all the other Stack Exchanges in terms of its structure. That structure is going to come down to us as XML and a very simple text. In order to do anything with it, we're going to want to clean that data. So coming up next is a chapter on cleaning data. But to conclude this one, I just want to thank you.